In this lecture, we're going to go over trusses. Trusses are two force members that are connected by pins, and each member can only have axial loads. That axial part is going to become important. So a truss element is similar to a spring element and all the other elements that we've done up until this point, where our force is equal to our elasticity times our cross-sectional area divided by the length of our member times our displacement. Again, we can think of EA out over L as an equivalent spring constant. So if I consider a single truss element, I have my displacement and force at each end. I have my stiffness, which is EA over L, and I have my displacement and force at the other end. Now, so just like for springs, we can write our force displacement relationship at each node. So the force at node 1 is equal to EA over L times the relative displacement of the two ends. And the force at node 2, again, is equal to EA over L times the relative displacement of the two ends. And in matrix form, we get that our forces are equal to our stiffness matrix times our displacement vector. Now, if like everything else we did before, all of our trusses are lined up on a single axis, we would have one coordinate system like we did before, and everything would be exactly the same as our discrete systems work. However, trusses are two-dimensional by nature, so we have to assign a global coordinate system, which we are going to name XY, and also establish a local coordinate system, X bar, Y bar. For each truss, we're going to have a set of local forces and a set of global forces. So what do I mean? Here we have our coordinate system, XY, that's our global coordinate system. And I'm going to draw a random truss member. It has a certain length H. It has ends 1 and has ends 2. This member is offset from our x-axis by some angle theta. And it has a coordinate system defined along it as X bar and Y bar. And at the two ends, we have a displacement U bar 1, F bar 1, and we have a second displacement U bar 2 and F bar 2. So U bar 1 and U bar 2 and F bar 1 and F bar 2 are similar to how we handled our discrete systems, which were one-dimensional, and they are along the axis of our member. So I can rewrite my force displacement relationship as F bar 1, 0, F bar 2, 0, where what I'm doing is I'm forcing the forces that are perpendicular to my member to 0, because a truss can only have axial forces. So this is axial, this is perpendicular. So we'd still have our EA over L properties. And this time our matrix is now 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0. So our original 1, minus 1, minus 1, 1 matrix is still there. We've now just expanded it to include both the X and Y bar directions for each end of our member. And this would be multiplied by our displacements. So we have U bar 1, we have V bar 1, where V is the displacement in the Y direction. We have U bar 2, and we have V bar 2. So I've expanded our system to no longer be one-dimensional. And again, want to point out, so we have U is our displacement along X bar, V is our displacements along Y bar, KE, which is all of this. This is KE now. KE bar, technically because it's local, is the element level stiffness matrices, and this, our displacements over here, can be called delta bar. Again, as a reminder, a truss is a two-force member, and at this stage we're setting the values in the Y direction to 0 because trusses cannot have perpendicular forces, so there's no Y bar directions in the local coordinate system. Well, that's great. We can do a calculation for a single truss member, but when do we really have a single truss, a single member truss? That wouldn't be very effective. What we need to do is a way to go from, okay, I have these equations that work for one truss along its local coordinate system, and relate that local coordinate system to the global coordinate system. So if I have a truss that has 7 members, I know how to relate all the displacements and forces for these members. How are we going to do that? Well, we're going to do that with some coordinate transformations. We need to convert our local force deflection relationships from local coordinates to global coordinates. So if we look at the figure of our member again, we have our forces in the X and Y bar along the member. We have our displacements in X bar and Y bar. But we also have the rotation of those. So not only do we have F2 here, we have F2X, and we have F2Y if we break it down into its components along our global coordinate system. So we'd also have a U2 and a V2, which are the displacements in the global coordinate scheme, not the local. So bar is local. So this is local. This is global. So how do we do that? How do we go from local to global? Well, we can say that, X bar is X cosine theta plus Y sine theta, and we can say that Y bar is minus X sine theta plus Y cosine theta. We can also write the reverse where x is x bar cosine theta minus y bar sine theta, and we can say that y is x bar sine theta minus y bar cosine theta. So I can transform from one coordinate system to another coordinate system using my angle of rotation. And if we put this in matrix form, because we love matrices in this class, we'd have x bar, y bar is equal to cosine theta, sine theta, minus sine theta, cosine theta, times xy. So this would give me my local coordinate systems from my global coordinate systems. And I can also do it the other way, where xy is equal to cosine theta minus sine theta, cosine theta, times my local. So I can go from global, I can get to local, and from local I can get to global. So the above relationship holds not just for the axes themselves, it also holds for the displacements and the force vectors as well. So to transform the local displacements into the global displacements, to transform the global displacements into local displacements, we're going to use our transformation matrix TE, and what that is so my local So my local is going to be cosine theta, sine theta, minus sine theta, cosine theta, 0, 0, 0, 0, 0, 0, cosine theta, sine theta, minus sine theta, cosine theta, times our global coordinates. So that's going to be u1, v1, u2, and v2. So this is our global, and this is our transformation matrix TE. A shorthand way of writing this is saying that our local displacements are equal to our transformation matrix times our global displacements. I can basically write the exact same equation for forces, so I can say my local forces are equal to my transformation matrix times my global forces. What I'm going to do now is I have my coordinate transformations, I have my local relationship. I'm going to see how I can use these two to generate my global stiffness matrix. I'm going to derive the global level. So on the local level, we had F bar is equal to K bar delta bar. So I'm going to replace F bar with my transformation matrix times my global forces. It's still going to be equal to my local stiffness matrix. And I'm going to replace my local displacements with my transformation matrix times my global displacements. Now, I have a transformation matrix on both sides of the equation. I want to get rid of that pesky TE that's in front of my F. And if we remember from linear algebra and linear systems, the way we're going to get rid of that is by multiplying the entire equation by the inverse or the transpose. In this case, they are the same. So I'm going to multiply everything by T transpose. So T transpose TF, let me put my little e's in here. It's going to be T transpose K bar T delta. So those two cancel out, they become the identity matrix, and we are left with our forces in our global coordinate system is equal to K times delta, where I'm saying K is equal to T transpose K local T, and this is your element level global stiffness matrix. So this is still only for a single element. We haven't added any elements to our truss system yet. We're still looking at a single element. What we're doing is we're now expressing the forces and displacements for this single element in the single coordinate system that's going to consist of all of our elements.